Hi, I'm Saurabh Mistry and I'm doing my PhD in the Aerospace Department of IIT Bombay, currently in my third year, and I'll be taking AE 314 and 727 and the Izod experiment. Why Izod impact test? It was to measure the impact energy absorbed before a fracture. What is energy impact? That is the work done to fracture a specimen. Now we'll be looking at two major types of specimens, that is brittle and ductile. So what difference will we majorly observe? So ductile material can undergo plastic deformation. Hence it can absorb a lot more energy before it actually fractures. Since brittle materials have a very small ductile region, we may not see this. We'll be looking at two types of materials or specimens. One is fiberglass, the other one is aluminium. Now when we perform the test, we are going to see the energy absorbed due to the fracture. So this area that is shaded here is where the fracture occurs. We will be measuring the area of this and that will be used in the calculation for the energy impact. This is the Izod impact test machine. I'll just explain the different components of the machine. We start with the hammer. So there are 4 different hammers on this machine. This one is a 25 joule hammer. Take note, I am not mentioning the weight, I am directly mentioning the energy, and I'll explain why. The next component are these 2 levers. One is a safety latch and the other one is to release it. So for example, I will first pull the safety latch and then I will release it. This lever over here is the brake. So when I apply the brake, it will slow down. Now why are we using this arrangement? Take note, if I release it from here, it will come to the same height on the other side. If I keep the specimen over here and it breaks, certain amount of energy goes in breaking it. So what height it will start from here is not the same height that it will come over here. That is why we have a scale over here, which I will explain when we zoom into it. This is the dial and I'll explain the different components of the dial. Firstly, the hammer starts from here. So when the hammer swings, it will take a full round and it will come back to this point. That is why all of these points are marked as 0. So if there is no energy loss in the swing, it will come up to the same point. So what you see here, you can see this moves. It contacts the blade. So the blade starts here. When it moves, it contacts the blade and it pushes the blade. If there is energy loss at this point, and let's say it only comes up to this point, then it will swing back. So what we notice is the blade gives a reading of certain joules. So this sector here is the energy lost. So if there was no energy loss, basically it would have come all the way up here, but it has not. Now you notice there are many different scales. The first scale is a simple degree scale. The next scale is, to make calculations easier, they have given 4 different hammers of different, not weights, but they've already mentioned the energies. So we have installed a 25 joule. So that is the third scale. So we will look at the readings of the third scale. Now we'll be performing the actual experiment. And as you know, when this hammer swings, it should come to the same position when there is no specimen. But as you know, the bearings etc. might have friction. So we first need to do a dry run and see how much energy is lost due to friction, and then we subtract that from the energy lost when breaking the material. So now we'll actually perform a dry run. So this is the needle. I'm moving it, you can see it. Before every run you have to bring it all the way here. This is the safety latch. Make sure nothing is in the way of the hammer. Release the safety latch and release the hammer. Now we've just oiled it before doing the experiment, so the reading is showing exactly 0 joules. Of course it will not be exact 0, but that means it's minuscule, so we can ignore it because we just oiled it today morning. Now the next thing is we'll actually put the specimen and then we'll see how much energy is lost when we break the specimen. The first specimen we'll be looking at is the fiberglass specimen. Now we will be mounting the specimen. So we take this back. So you can see the position of mounting. Do not over tighten or you get residual stresses within the material itself and you won't get accurate readings. Please take note, before breaking it, for every single specimen, we have to take the measurement of the length of the notch and the width of the notch, and that is what will give us the area. Each specimen is manufactured, so of course they will not be absolutely identical, so you have to do it for every single specimen on its own. We have installed the fiberglass specimen inside. Remember this needle, I am moving it, I am sure you guys can see it. It has to be rotated and put in the start position before every run. And now we will break the fiberglass specimen and see how much energy is absorbed in the break. This is the safety latch once again, and release. Now we will take the readings. Like I said, this is a 25 joule hammer, so that's the third scale, and the reading is 2.2 joules. Now remember, you all had calculated the area of the cross section, so that means 2.2 joules was used to break that particular area. So now you can calculate the energy used to break the specimen per mm square. That is the energy impact. The next specimen I will load is aluminium. So once again I bring this to the top. I remove the broken specimen. We'll take a close-up of this also for you all to see clearly. We finished the fiberglass specimen. Now we've loaded the aluminium specimen. Always remember to take the needle to the start point. Release the safety latch. Yeah. So as you can see, the specimen has not even fully broken because the hammer has not even come this side. So we are measuring an energy loss of somewhere near 23.8 joules. I repeat, 23.8 joules. The next is we'll actually show you a close-up of both the specimens breaking. These are the two specimens that have been broken. You can see the different types of fractures. Now the fiberglass is brittle, so it has not gone into the plastic region at all, it has directly just sheared off. So it's a clean cut. Whereas if you look at the aluminium specimen, you can see a lot of necking. So this is why the aluminum specimen absorbs so much of energy before it breaks, because it is ductile. Now the way to calculate is, we know the energy, we've seen it on the dial, divided by the area. That gives you the impact strength of each material, and we will provide you all with at least 10 specimens or more if possible, the data of them, and then you all have to actually calculate the impact strength and also see the variance of the materials. Now since fiberglass is a more involved process of manufacturing, you might see more variance in the results. So keep an eye out for that. This is the observations page. Under specimen name, you either fill aluminium or fiberglass. The width is the width of the notch and thickness is the thickness of your specimen. Energy is the reading that you get off the dial, and impact strength is energy divided by the area. So that's J divided by width into thickness. Type of failure, it depends on the material. You can either write ductile or brittle failure. To submit your assignment, you have to submit the following answers. Why do we need to do an impact test? Can we find fracture toughness using stress strain curve? Note your observation about the scale of impact testing machine. Name some applications of the impact test.